In this tutorial, we will go over how to implement a driver for an array of WS2812 LEDs, otherwise known as Neopixels. These Neopixels use a single wire PWM signal to pass a total of 24 bits to each LED in order to control them. These 24 bits are composed of the red, green, and blue or RGB values of each LED. This unique single wire protocol can often be implemented in software. However, the software implementation of this presents two potential issues. The first being that data transfer would need to be handled completely by the CPU. Any break-in data transferred to the LEDs will cause unwanted visual results or lagging reactions. This also means that no new frames can be generated since the CPU is occupied updating the pixels. Therefore, multiple cores would need to be run. One completely dedicated to sending the correct data format to the Neopixels, and another for generating the next frame or any other processing you would like to do. The second potential issue is that an extremely fast clock frequency will be needed to execute code fast enough to give smooth and seamless transitions to your Neopixel array. This could greatly increase the cost of your design and greatly increase the power consumption. However, in this tutorial, we will discuss a hardware-based alternative to this software-intensive implementation of a Neopixel driver. So if learning how to implement a Neopixel driver on an 8-bit device is something that you would like to do, please continue watching. I have my MPLAB Express project configured for the PIC 18F46K42 and my MPLAB code configurator opened. The configurable logic cell peripheral featured on devices in the K42 product family can be used to combine other peripheral signals into a single signal that the Neopixels can understand. We will first start by configuring all of the inputs for the CLC. I will start by changing my clock to high frequency internal oscillator. I'll also change my clock speed to 32 MHz. Additionally, I will change my clock divider to 1. Next, I will add a timer 2 peripheral. This will be one of 3 peripheral inputs that I will feed to the CLC. In the timer 2 peripheral, I will change the clock source to FOSC divided by 4 and change the timer period to 625 nanoseconds. Next, I'll add a SPI module. I will change the operating mode to master and also change the clock source to timer 2 post-scaled. I also need to navigate to the registers tab to do some further modification. According to the datasheet, when TXR is set to 1 and RXR is set to 0 and B mode is set to 1, the SPI module will operate in transmit only mode. Therefore, in MCC, I will change B mode to every byte. I will also change RXR to data is not stored in the FIFO. This disables the bit. Additionally, I will make sure that TXR is set to required for transfer. With this configuration, data will be transmitted as soon as the TX FIFO register is written to. The last peripheral that will need to be given as an input to the CLC is a PWM. Once this has been added, I'll ensure that the timer is set to timer 2. Now I will add the CLC peripheral. I chose CLC 3 because I would like to use port RB1 of the Express board as an output to the LED array. However, any of the CLC modules can be selected. We can now use the SPI and PWM peripherals to generate a logical expression needed to mimic the serial protocol used by the Neopixels. An app note that further explains this equation is provided in the description below. In order to generate this expression in hardware, I will first set source 1 to PWM5. Next, I will set source 2 to SPI SCK, source 3 will be set to SPI SDO, and the fourth source will remain unchanged. I will place inverters on the first 2 inputs of the first OR gate. Additionally, I will place an inverter on the output of the OR gate. I will also place an inverter on the third input of the second OR gate. I will enable the second input on the third OR gate, and I will enable the third input on the fourth OR gate. One of the last things that we need to do is configure our pins. Navigating to the pin manager, I will set the output of CLC3 to RB1. Additionally, I will verify that RC3 and 4 are set to SCK and SDI. And lastly, I will remove the input pin from timer 2. This should be all that we need to do to configure our LED driver, so I will go ahead and click the Generate button. The first thing that we are going to do is implement a function to write to the LEDs. This will take in an R, G, and B parameter. As mentioned before, the SPI will transmit anytime the TX buffer is not empty. Therefore, we will write the green value to the TX buffer. After this, we will wait until the TX buffer is empty before sending anything else. We will do the same for both the red and blue color values. For this example, we will light the first 24 LEDs of the Neopixel array. The Neopixels are wired in series. Every 24 bits sent over the serial communication is used by the first available LED. If the LED has already been written to, then the data is passed on until it reaches an available LED. I will first write a for loop to clear all 256 LEDs by writing zeros to the RGB values. I will also add a 1 millisecond delay to allow the LEDs to reach their latch state. I would like to set the first 24 LEDs of the array to green. Therefore, I will need to write a for loop to write a green value to every single LED up to 24. After I make and program the device, you can see that our custom peripheral serves its purpose in generating a signal that our Neopixels can understand. Through core independent peripherals, we were able to create a custom signal for our Neopixel array. This hardware implementation greatly reduces the amount of responsibility on the CPU. The same technique can be used as a building block for more complex array manipulation. Express examples online show how to take what we did in this video a step further to implement scrolling text on this 256 LED array. For more information on using Neopixels with PIC microcontrollers, please see the link provided in the description below.